They informed me that this physics essays volume that is a memorial volume or honorary volume for Ugo Fano, in which he did have some contribution in evaluating the contributions. This is available. It's $40, and you should see Midio if you want to take one home with you. He has a few with him, but you can certainly order one from him. So if you're interested, please see Midio Inakuti. Now, I'm supposed to give some introductory remarks, and I did prepare them, but I can't really get this working very well. So maybe I won't. Maybe you'll be lucky, and I won't give them. Get that. Yeah. Let's see if we can open it. Okay. Now go under Documents. Documents. This one, right there. Okay. And then Collective Dynamics.
Let's see the military.
Hey, this is a good pointer, right? My finger. And then ITAMP. There. Let's see what happens.
Yesterday.
See if it comes up.
Yeah.
Okay, then come under the slideshow and get it going. Hit slideshow.
Where's that?
Here. Slideshow.
Down the bottom.
There you go.
Right there. View show. Okay. Hey, with the help of the local experts, it accidentally worked. Okay. I'm going to introduce this session, and I'm going to try to set a standard and keep my remarks brief, although somehow Microsoft PowerPoint won't let me do that. But our topic today, or this morning, is collective dynamics, which of course was a concern of Ugo Fano for a very long time, and on which he made some of the really basic contributions. And one of the contributions that he made that I've always thought was, in a way, rather insightful was he introduced the correlation coefficient. He, first of all, introduced the idea that when you have any kind of process, that process prepares a state. And you can actually define it if you like, but if you have a process represented by some transition element, that prepares a state. And if you prepare the state with two different processes, you prepare a state with two different processes, then there is a correlation coefficient, which is the overlap of those two states. So that's the simple definition of the correlation coefficient. Very, very elegant and very simple. I'm going to focus on the state that's prepared by the process because that sets the tone for some of the things we'll discuss. And there's always one state prepared by the process, but if there's a whole bunch of other states, which there usually is, they are all, there's a whole set of states that are orthogonal to the one that's prepared by the process. And then this is the very general sort of unitary transformation that Ugo introduced, but he used it, one of the uses that he made of it was to give new insights into partial wave expansions. You wouldn't think you could get new insights into partial wave expansions, but Ugo did. He said, consider a particular process where the transition matrix is roughly like a delta function, and we consider the free particle states. Then if you go through that procedure, the state that's excited by the transition is approximately a constant as the radius goes to 0. And then there's all the other states. All those other states, because you've subtracted off the one that's excited, all those vary linearly with R. But now you can repeat the procedure. You can take this set that varies linearly with R and repeat it with another transition operator that basically subtracts off those that go linearly with R. And so you get a second one that goes linearly with R, and then all the others go as R squared. And you continue this, and you get to the end, you get the partial wave expansion. But it's not quite the partial wave expansion. It's a partial wave expansion with a totally different interpretation. It makes no use of spherical symmetry. Spherical symmetry never came in. It just is a matter of states excited by a process. But of course, symmetry comes in. And symmetry comes in because we've focused on near the origin, symmetry comes in because as the waves travel away from the origin, then if it's in a spherically symmetric potential, if you put them in the right spherical states, they'll stay there. So that's where spherical symmetry comes in. But of course, as you know, very few systems are really spherically symmetric. Fano was really interested in the solids and condensed matter. As they go out, you lose the symmetry, and so there's some interchange, but that propagation outward is where some of the dynamics occurs. But for spherical symmetry, we get partial waves of a definite L. And more generally, and on the basis of this, Fano really went off into two different directions. One is, as you go out, you have to go into maybe different channels, and that's a frame transformation. And we'll have some examples of that in our talks today by Chris Green and Mike Cavagnaro. But more generally, you bridge into different regimes, and this regime actually, Giancarlo Stannati has actually developed this idea with Ugo, that as you propagate, you get into the macroscopic regime, and the connection between microscopic and macroscopic is something that Giancarlo will talk about. But the other topic, which is sort of why I'm chairing this session, is that Fano really wanted to extend these ideas to any number of particles, not just one. The partial wave was just one particle, but you could go to many particles via hyperspherical coordinates. You introduce a hyperradius and then go through the same procedure, but now you do it in hyperspherical coordinates, 3n coordinates. And of course, according to this, you'll get hyperspherical harmonics, just like you got partial wave expansions. And Ravi Rao wrote several important papers with Ugo on this topic. But for multiparticle, as the multiparticle wave travels from small r to large r, the difference between the spherical case and this case is it has to branch into the physical channels. Now, Fano had gone through several attempts to find a good way to figure out how it branches into different channels. At the moment, it's still true that using an adiabatic picture, where it adiabatically moves into these different channels, seems to be the only practical way to implement the picture, to do quantitative calculations. And now this picture is now, thanks to work by Shinichi Watanabe and Chidong Lin and a whole host of people in Japan, it's fairly complete for 3 particles. But, of course, it is more general than that. It goes off into any number of particles. And the difficulty in more than 3 particles, well, it's just beginning in more than 3 particles. You first have to develop methods to compute the adiabatic basis, and Duarte Bloom, who gives our first talk, will describe computations for clusters of atoms, so that's n particles. And Dr. Morishita will discuss 3 and 4 electron atomic species. But in addition to computing the adiabatic basis set, you have the problem that when you go to the more particles you have, the more channels you have. And then you have the problem after you get the adiabatic basis, then how to treat all the channels, the large number of channels. Well, that hasn't been solved because the first problem hasn't been solved. But at any rate, how to treat large numbers of channels, you have to find all kinds of systematics. And Morishita will tell us, in the context of the 3 and 4 electron species, will tell us a little bit about the progress that he's made in selecting and classifying those channels. So that's basically our session this morning. And with those remarks, by the way, I should, of course, thank Hussein for doing all the legwork of organizing this and actually asking me to be a participant. I've always considered since I was never a student of Ugo Fano, I felt myself one of his illegitimate children, not one of his children. But at any rate, so with that, I thank and to turn it over to Duarte Bloom will give the first talk on, let's see, the title. You'll have to give the title. Oh yeah, right. You need the mic.